Bismillahirrahmanirrahim. In the name of kind Allah. Assalamu alaikum. How are you, students? Again, Faizullah Omar with you. Today we are going to study transition elements. Okay, first of all, let me define what's the transition elements. The name transition element is given to the D block elements because of their position between S and P block elements. Or we can say that transition elements are elements that are located between S block and D block elements in the periodic table. Let me show you where is the location of these transition elements. This is the modern periodic table of the elements. You can see that these two groups or columns are known as S block because their electronic configuration lasts in the S orbital. And from here, from 13 to 18, these groups 1, 2, 3, 4, 5, 6. This sixth group is known as P block elements because their electronic configuration finishes or lasts in the P subshell or the orbital of the P subshell. And from here, from 3 to 12, these groups are known as D block elements or the transition elements. Now you can see that from here to here, 3 to 12, this is located between the S block and D block element. That's why we call it transition elements. Okay, students, let's study the property of transition elements. As I've told you that the transition elements are situated or located from group 3 to 12 in the periodic table. Okay, you have seen that. And let me tell you the next thing, all metals, they're all metals in the transition elements like copper, iron, zinc, silver and gold. These metals are located in the transition element or the D block of the periodic table. Yes, all of them are metal. And let me tell you the third property of these transition elements. As we know that metals are dense and hard, so all the transition elements, maybe there could be some exception, but normally all of them are dense, their density is very high and they are very hard. And the next property, they are malleable and ductile. What's the meaning of malleable? Malleable means, it's a kind of property of metal. Malleable means if anything is capable of being extended or shaped by beating with a hammer, we call that thing malleable. If you beat iron with the hammer, it will become very thin, and with the help of hammer, if you beat it again, you can turn it into a very thin foil. Even gold, silver, all of them. And ductile means if they are drawn out into wires, that's ductile. For example, we can make wires from the metals, from these transition elements. That's why we call them ductile. And all of them are solid, except Hg. What's Hg? It is mercury. Except mercury, all of the transition elements are solid. So remember this. And we know that one of the properties of the metals and the most of the good metals are situated in the transition elements, they are good conductor of heat and electricity. Okay? And the next thing is they have very high melting and boiling point. They would not melt in a normal temperature. If we need to melt these transition elements, we need very high temperature and to boil them. And the next and the last thing is that they make 60% of all known elements on the earth. Okay, these are the properties of transition elements. Let's go to the next. What's the general electronic configuration for transition elements? The general electronic configuration formula for the transition elements is NS1 to 2 and N-1D 1 to 10. Or vice versa, we can say like this. Sometimes you may have seen something like this. N-1D with the power of 1 to 10 and NS 1 to 2. Okay, this N shows the principal quantum number. S and D shows the orbitals of the subshell or secondary quantum number. And 1 and 2 and 1 to 10, these are the number of electrons that are present inside the orbital of these elements. Let me show you an example. For example, we have cobalt over here. The electronic configuration of cobalt is argon 4s2 3d7. Why we call it argon? Because from here 1s2 to 3p6, This is the electronic configuration of argon. We can say something like this: 1s2, 2s2, 2p6, 3s2, 3p6. This shows the electronic configuration of argon. Argon is a noble gas. Remember, students. So argon 4s2, 3d7. Okay. If you remember from the electronic configuration, we have studied that the relative energy of 4s is smaller than 3d. So 4s will fill first, and then next is the turn of 3d. Okay, students, that's normal. But there are some exceptions in the transition elements. Transition elements are very complicated. For example, chromium and copper. There's an exception. Let me show you. 1s2, 2s2, 2p6, 3s2, 3p6. From here to here is argon. I've written argon. Then 4s1, 3d5. I've told you in electronic configuration that 4s will fill first. It should be 4s2, 3d4, but it's not like that. This is the exception with the chromium. And if you come for the copper, you can see that from here until 3p6, it's argon. And then 4s1, 3d10. Why? Is still there is an exception. Because there, if it was normal, we should have to say that 4s2, 3d9. But it's not like this. So these are the exceptions that are found in electronic configuration of the transition elements. Okay, when it comes to the chemical reaction, what happens with the transition elements? Do they lose electron or donate electron from the s orbital, 4s orbital, or 3d orbital, if we are talking about the cobalt? Let me study this. Relative energy of 4s is smaller than 3d. We know that. That's why 4s had to fill first, then the 3d. But these are exceptions. We are not talking about the exceptions. But contrary to the rule, transition elements donate electron from 4s before 3d. For example, if cobalt is going to react, cobalt will lose these two electrons before the electrons from 3d. Cobalt will lose the electron from 4s before losing electron from 3d. Why? What's the reason? Because the energy difference between 4s and 3d is not much higher. They're around same. While filling, 4s will fill first and 3d will fill next. I am not talking about the exception again. And when they lose electron, again the 4s will lose first and 3d will lose next. Okay, let's go to the next topic. What about the atomic radius of transition elements or the D block elements? You can see over here, if we talk about the fourth period, it starts from scandium to the zinc. The atomic radius is decreasing again until the nickel, and then it started increasing again. You can see that the atomic radius, or their metal, so we can also call the metallic radius, is the metallic radius is the 2 times of atomic radius. Okay, so metallic radius in the scandium is 162 picometers or 61 picometers, and in nickel it's between 120 and 130, so it must be 124 picometers, the metallic radius. And then in zinc, it's again getting high, going high. It's around 134 picometers. Why is this happening? Because if this had to fall down, it must go falling down until the zinc. But again, it's getting high. What's the reason? Actually, in atomic radius of transition elements, first decrease from left to right and then slightly increase. The decrease is due to increase in nuclear charge of element and number of electrons. As we go from left to right, the nuclear charge will increase. We know that the atomic number of tin is higher than scandium. It has more proton and more electron. So, which means that there will be more attraction between the nucleus and the electrons. So, atomic radius must get smaller. We have studied in the atomic radius lesson. Okay, so it's getting smaller until the nickel because of the strong attraction between the outermost electron or valence electron and the nucleus. And why it is slightly increasing over here? It is because of the crowd of electrons in the D subshell. Over here you can see that in D subshell electrons are increasing, and because electrons have same charge. Now electrons start to repel each other. The repulsion of electron causes that the metallic radius gets a little bit higher or bigger. There's a reason that you can see a slight increase from nickel to zinc, copper and zinc. You can also see same thing in the other periods of the transition elements. And let me tell you again, metallic radius is the distance between two metals. For example, if I say about the iron, if two atoms of iron are located beside each other, the distance between two nucleus of these iron will be the metallic radius. So half of the metallic radius will be the atomic radius of iron. For example, for iron it's around 126. So what will be the atomic radius of iron? If we divide 126 by 2, it will make 63. So 63 picometers will be the atomic radius for the iron. Let's go for the oxidation states or the oxidation number of transition elements. Actually, transition elements can have many oxidation states. For example, in fourth period, we can see that the 4s and 3 orbitals are very close according to their energy, as I have told you before. And electrons from both s and d orbitals can take part in the reaction, resulting various oxidation numbers of a single element. For example, for scandium, it is plus 3. For titanium, it's plus 4. But when we come for the vanadium, it's plus 2, plus 3, plus 4, and plus 5, which means that vanadium can lose these 2 electrons and these 3 electrons as well. But when they start donating electron, when they start losing electron in the reaction, they start from the s orbitals. For example, for the vanadium, when it is plus 2, for the plus 2, it will lose electron from the 4s. And when it will be plus 3, it will lose next one, plus 4 and plus 5, which means that all the electrons from the last shell is, from the 4s orbital and 3d orbitals is empty now. If we have a look at the manganese, it has 5 oxidation numbers: plus 2, plus 3, plus 4, plus 5, 6, and plus 7. Okay, there are 7 electrons. 4s2 after the electronic configuration of argon, manganese has 7 electrons. 4s2, 3d5. At very first, when it is the plus 2, manganese will lose 4s electrons of the 4s orbital. And when it's plus 3, then it will start losing electrons one by one until it will get the plus 7 oxidation state. Okay, again, same thing with the other elements. Let me show you some example of the oxidation states of manganese. If we look over here, it's manganese oxide. Okay, oxide of the manganese is plus 2. We know that MnO, oxygen in oxide form, it is always minus 2. So which means that only 2 electrons from the 4s orbital of the manganese has gone. So it is plus 2. When it comes for the manganese trifluoride, you can see that there is plus 3 charge. We know that for fluorine is the only element which is always minus 1, and it won't donate electron to any other element. It will always gain electrons, so it's always minus 1. If we have 3 fluorine, which means that minus 1 multiplied 3 or minus 1 times 3, it will make plus 3. So manganese is plus 3 over here. And it come from the MnO2. MnO2 for oxide, I told you that it's minus 2. Minus 2 times 2 makes minus 4. To neutralize the minus 4, we will need plus 4 over here. And when we have a look in this one, for potassium, K3MnO4 is always minus 2. Okay, so minus 2 times 4, it will become minus 8. And potassium is plus 1 always. So it will be plus 1 times 3. It will make plus 3. Minus 8 and plus 3 makes plus 5. So over here, the number of oxidation of the manganese will be plus 5. Okay, when you come for our here, it's plus 6, and when we come for the last one, potassium permanganate, it is plus 7. So now we can see that there are various oxidation numbers present in the transition elements. Okay, students, that's all. We have finished our lesson today, and if you have any question or suggestion, you can write in the comment section below, and please don't forget to subscribe our channel and give a thumbs up. Thank you. Goodbye.